Alrighty. There's a fair bit of theory today, so and the same on Tuesday. There's a fair bit of theory for the next two sessions. So today's just another way of thinking about, talking about defining dy dx. So what we know is a few things about dy dx. So it's called, given its full name, it is the derivative of y with respect to x. All right, so give it its full technical name, that's what it is. What do we know? We know that dy dx is the gradient. Now another way of describing it is in terms of a rate, and it's also can be thought of as the rate of change in y with respect to x. All right, so if we're looking at the rate of change in something, then what we need to think about is what they're talking about is the derivative. All right, so once we've got that definition, all is good. All right, so dy dx, full technical name, derivative of y with respect to x. In terms of what does that represent for us, represents the gradient, also represents what's known as the rate of change. All right, so when x changes a bit, y changes a bit. How much? So just like, for example, on a graph, there's a line on the graph. So if we're going here and x changes from there to there, so we now got this point, what's the change in y? So what's the rate of change in y when x changes? That's what it's meaning. All right, so let's get a bit more specific. With that. So there's two rates of change. So let's look at for the function with the rule fx, function of x. So the two types of rate of change, first of all, it's the average rate of change. So when x changes, say, between A and B, if I do a little rough sketch, So we've got some curve, for example, and x equals a is here, x equals b is there. So we're going from this point to this point, and so the gradient, so remembering the rate of change is related to the derivative, which is related to the gradient. So between A and B, the gradient's actually not the same, it's changing. So the question's asking us about here the average. So when it talks about average, what we need to think about is the straight line that joins those 2 points, its gradient. Alright, so our average rate is the gradient of this line. Tessa will be in Merrill's class.
Yep.
Alright, so in terms of coordinates of those points, this point here would be B and f of B. Alright, so it's just putting x equals B into whatever the equation is. This point here would be A and f of A. So put x equals A into the equation to find the y value. And so our average rate then would be y2 minus y1 over x2 minus x1. Alright, so that's average. So the average, you're looking at the gradient of the straight line that joins the 2 points. Alright, the other type of rate of change is what's called the instantaneous. So in this case, you would have just a single point. If we look at, again, I'll draw another graph. It's that one curved like that. So if there's A, point A, so what we're after then is the gradient. Remember, rate is related to derivative, which is related to gradient. So what we're doing is looking at the gradient of that tangent. So the gradient of the tangent is derivative, and then we need to substitute A in. Yep. So our instantaneous rate equals f dash, the derivative, when we substitute A in. All right. So think rates, gradient, derivative. Average rate, we'll use that old y2 minus y1 over x2 minus x1 that we've been using for years. Instantaneous derivative. Alright, let's do some examples. Alright, am I right to rub that off?
Not the bottom bit.
Not the bottom bit, across my second T there.
Yeah, I know exactly what you're talking about. It's just like...
Alright, to rub that bottom bit out now, Zeke.
Yeah, go for it.
Alright, so solutions, average rate and instantaneous rate. So for A is the average. So when we're talking about the average, that is the difference in our Y values. So f of 3 and f of 2 over the difference in the x values, which is 3 and 2. And so now we need to use our equation, our function, put the values in, crunch the numbers. So 3 squared is 9, plus 6 is 15. 2 squared is 4, plus another 4 is 8. 15 minus 8 should be 7.
Isn't it 2 times negative 3?
Negative 3, by negative 3.
Isn't it? I just made that up.
Where you got negative 3 from, Glenn? I can't. There's no negative 3 there.
Like
3. That's all right, Glenn. It's early in the morning. All right, 15 minus 8, 7 divided by 1 is 7. So the average rate between those points is 7. So what does that mean? It means when x changes from 2 to 3, then the y value changes by 7. So it changes from 8 to 15, which is a change of 7. All right, part B. To do part B, what do we need to do?
Put it in the other one.
Differentiate and
Substitute.
substitute. All right. So we're after f dashed of 2 then. So what's the derivative? Let's get that first.
2x plus 2.
2x plus 2, yep. So f dash 2 then, 2 times 2 plus 2, which is 6, I hope. All right. Couple more examples. So one of the things that's mentioned in the study design is a thing called Newton's law of cooling, and that has to do with rates. So, in other words, how quickly something is cooling.
We don't need to know that.
You don't need to know the equation for Newton's law of cooling, no, but you need to be able to.
So they're halfway into the book. It's 14.
Yeah, so you don't need to know Newton's law of cooling off by heart, but you need to know how to apply a rate to that. All right, so what we are going to do is, and a question that is in your textbook. I don't have to write out all the... We don't spend time writing out all the words.
What page is it on, Mr. Simmons?
Yep, 423. So, example 9, page 423. Alright, so it says the pot of liquid put on the stove. When the temperature reaches 80, the pot's taken off and placed on the bench. The temperature in the kitchen is 20. The temperature of the liquid is T at any time, sometime T minutes, and you're given the equation. So we're told that the temperature at any time will be, 20 plus 60 e to the negative 0.3 T. So the 20 here, just to highlight, the temperature in the kitchen is 20 degrees. That's this 20 here. We're told that it gets heated up to 80, so if time equals 0, anything to the power of 0 is 1. So 20 plus 60 gives us the 80. All right, so these numbers that are here are not just random numbers, they relate to the information. All right, the question says, find the rate of change with respect to time in terms of T. So if we're talking about the rate of change with respect to time, of the temperature with respect to time, that means we need to starts with D.
The derivative.
Derivative, thank you.
But in respect, like, it's not T.
All right, so the rate of change of temperature with respect to time, dt, big T, d little t. All right, two terms. This term here, when I differentiate 20, I get
1. Oh, no, yeah,
0. Any number, just a normal number, when you differentiate, becomes 0. All right, here, 60 times what? E to the...
0 point.
Yeah, that doesn't change. All right, so I can neaten that up. And when we do that, 0.3 of 60 is 18 apparently. All right, so there's part A. Let's have a look. Let's just... Yeah. Let's read the question again. It says, find the rate of change of temperature with respect to time in terms of big T, so in terms of temperature. Now I've got time in here, so I haven't actually finished the question.
Oh, great.
Because it asks for that in terms of the temperature, not the time. What do you notice about this bit? It's in this bit here too, isn't it? Yeah. So, what I'm going to do is I'm going to get that by itself, and then whatever I get, replace it in there. Alright, so let's do that over here in, let's do that over here in blue. So if T equals 20 plus 60 e to the minus 0.3 t, where I'm going to move first?
20.
20, good. 60 e to the minus 0.3 t. And then the 60, so I'll divide by the 60. All right. And so now, this bit here, I'm going to put there instead of that e to the minus 0.3 t.
How are we supposed to be determined?
Right. And so what have we got? We've got 3 goes into there and there, doesn't it? 6 goes in as well. Then we end up with -3 outside of t minus 20 over 10. So now our rate is in terms of temperature. All right, so when you get to the exam, you need to make sure when you've got an answer, like I had here, that you just go check what the question's actually asking.
The answer's still not the same.
Still not the same.
fully.
Oh, they just divided it by
Yeah.
10, so it's 0.3, and then they took away the negative, so it's 20 minus 2.
Same.
I hate it when they take it. Why
Alright.
would they even bother taking mine?
So the answer in the book and this answer are versions of each other. So unless they are asking for a specific form for the answer, that's good.
So could you
All right.
just give your answer in the form of the question? Could
You
just
should give your answer in the form of the question, yeah. All right. Next part says, Part B, find the rate of change of temperature with respect to time when the temperature is those particular values. All right, so we're now going to use this. Substitute the temperature. On the exam, this question more than likely, because you've got to use this to do the next part, would be more than likely one of those show questions. So that, you know, you're showing something and then you're going to use that. So rather than, because you need to use that, you're disadvantaged if you can't get this answer, you're disadvantaged in doing part B. So would probably be a show question in the exam.
Show that this equals this.
Show that this is equal to this or whatever's in the, or that answer in the book. Because if you can't do part A, you can still do part B. So they avoid asking questions where if you don't get part A, you can't do the rest of the question.
Oh, so it'd be like show that da 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 equals that answer.
So, yeah, show that that equals that.
Yeah.
And then it'd say hence or otherwise, blah. So you need this to do this. And
Yeah.
so when they write the exams, they avoid doing something where you're
get
going
it
to be
all wrong.
disadvantaged for the rest of the question if you can't get this first bit. So that's what then they need to show. So whenever on the exam it says show something, and then it says the next bit, hence or otherwise, but hence or otherwise is meaning you're going to use what you showed up the top. So if you couldn't show it, it doesn't matter, you can still use that thing. All right. Let's look at part B. So part B, there's our time. It's our change in temperature and time. Part B, number 1, says when temperature is 80. So when temperature is 80, we put 80 in. And you would get -3 times 60 over 10, which is -18 degrees Celsius. I'll give you a unit for time. No. Oh, minutes. So what does that mean? It means that when the temperature of the liquid's 80 degrees Celsius, its temperature's changing by 18 degrees Celsius each minute at that specific time. Part 2, when the temperature is 30. When the temperature is 30, we put 30 in. And we get -3 degrees Celsius. All right, so when the difference in the temperature and the surroundings is greater, the cooling rate is more, and that's what Newton's law of cooling is about. Now, you'll notice both of those are negatives. What does the negative mean, do you think? It's cooling down, yep. Let's spell right. All right, one more application of rates of change is for motion. Right, am I right to rub all that off? So motion in a straight line is another application. So for motion we use these quantities. position, where something is, usually is x in maths. Velocity, v. Acceleration, which is a, and time, which is t. All right. Now these four things are related to each other, and they're related in the following way. Velocity v is the rate of change in position. And time is the thing that links all of this together. So rate of change in position is the rate of change in position with respect to time. So how fast something's going, and also the direction as well. Acceleration A is the rate of change in velocity. And again, it's with respect to time. All right, so is it speeding up or slowing down? Or staying the same? All right, so for us, we need to know these things and then use them. Now, in maths, in terms of direction, we don't have to be too worried about the direction, because then the mathematics takes care of the direction, and it's just like plus or minus, unlike physics where you may have other directions, north, south, east, west, whatever, up, down, left, right. All right, again, so we don't have to write down a whole bunch of words for the question. I'll do one out of the textbook. All right, to rub this off. All right, so example 10, page 424. Alright, so I've got a bunch of words there. A particle moves along a straight line such as position, x metres relative to point O, time t seconds is given by the formula. Now, sometimes people get hung up about where this point O is. Don't worry about where point O is. You don't need to know where point O is. It's just some place that these measurements are being taken from. What we do need to worry about, and we're given the equation. So t cubed minus 6t squared plus 9t. Right, so at any time you can find out how far away it is from this point we're doing the measurements from by just substituting the time in. And if it's a positive then it's in the positive direction, whichever that is. If it's a negative answer, it's in the negative direction, whichever direction that is. Now, there is an implied domain here in these questions. The implied domain in these questions would be
Positive numbers.
positive numbers, yeah. So t must be greater than or equal to 0. All right. Negative time doesn't make sense. Well, you could argue that it's in the past. However, you would then need to be assuming that it was moving in the same way in the past. But we don't know that. All we know is how it's going to move in the future. All right. Nice bit of waffle there. Let's move on to the question. At what times and in what positions the particle has 0 velocity? So there's a whole... It's talking about when, which is time, where, which is position, oops, is velocity equal to 0. Okay, so we need to break it down. First of all, that's the key when the velocity is 0. So we need velocity. We've got position. Velocity is related to position by the dx dt, the derivative. So the derivative of that is 3t squared minus 12t plus 9. Okay. And we're interested in what about this velocity?
When it equals 0.
When it equals 0. We're interested in when that velocity is equal to 0. And when v equals 0, we'll have 3t squared minus 12t plus 9 equals 0. That's right. So the velocity is 0 at a couple of different times. What times is the velocity 0? 1 and 3. All right. So the when part, we've now got the when part.
That be p squared in bracket 3 bracket t minus 4t.
Sure would. Now what I'm going to do? Yeah, so our when we found. How do we find the where? What's that, Erin? Great idea. All right. So when t equals 1, its position is 1 cubed minus 6 times 1 squared plus 9 times 1, which is 3 minus 6 plus 9 is, no, 1 minus 6 plus 9 is 4. Is that correct? And when t equals 3, it's 3 cubed minus 6 times 3 squared plus 9 times 3. And you work that out. You get 27 minus 27. 6 9s are 54, is it? 54 plus plus 27, which is 0. Okay, part B says its acceleration at these instants. Not so where, this is the where. Right, part B says the acceleration at these instants. So which instance is it talking about?
1 and 3.
1 and 3. So acceleration. How do we get acceleration? dv over dt. Yep. So we need that first of all. And what is dv over dt?
Rate of change in velocity.
Rate of change of velocity. And also, given the velocity is that, it would be 6t minus 12. Yes? 2 comes down, reduced by 1, minus 12, and the length gone. Alright, at those instants, let's find out what it is. Alright, so when t equals 1, acceleration is 6 times 1 minus 12, which is negative 6. Meters per second squared is the units. And when t equals 3, it will be 6 times 3 minus 12, which is 6. Just a note, this negative means, what do you think? Yeah, it's acceleration, negative acceleration. What do you think it's going to be? Slowing. Yep. All right. Part C. Its velocity when its acceleration is 0. Right. So first of all we need to find out whenabouts the acceleration is 0, and then we can find its velocity at that time. So acceleration we know is 6t minus 12 when that's 0. That occurs at what time? Add 12 divided by 6. 2. So we're after the velocity at 2 seconds, and the velocity equation was the one I've rubbed out. It's the 3t squared one. And so now we need to just put 2 in there. Crunch the numbers. 3 fours are 12, minus 24 plus 9 is 3. Yep. And all that negative there means it's moving in the negative direction, whatever the negative direction is. And we don't need to worry about what the negative direction is. All right, anything that I need to clarify there? Yes?
meters per second squared again?
And it's velocity, so it's just meters per second. So, yeah. So generally, for the units, position would be meters. Velocity would be meters per second. Sometimes you see it written like that. And acceleration would be meters per second squared, or ms to the minus 2.
Right.
But if they talk about hours and kilometres or something like that in the,
Yeah.
then you replace. But anything else? No,
Do you have to convert at all for the units?
not usually, no. No. So in maths, the emphasis is on the calculus
Yeah.
aspect of it, yeah. And this is an application of the use of calculus. In physics, we look at it differently, don't we?
As I was like,
Anything else? No? All right. 10B then.
It's the same. And then you get one of these.